You're about to embark on a journey that will question everything you think you know about reality, and I'm not exaggerating when I say that, because there's a scientific debate going on right now that calls into question not one or two isolated ideas in physics, but potentially the very framework we use to understand the cosmos. And it all started when Neil deGrasse Tyson, one of the most respected astrophysicists and science communicators on the planet, raised such profound questions about the nature of reality that even the most brilliant theoretical physicists were silent for a few seconds before to try to answer. Because we are not talking about a scientific theory in the traditional sense of the word, but about a set of philosophical and scientific questions that expose the absolute limits of what we can know about the universe using the tools of modern physics. And the central question that Tyson poses is devastatingly simple but deeply disturbing. He asks whether the laws of physics that we have discovered, tested, and validated for centuries are really universal laws, or just local patterns that our evolved mind in this specific corner of the cosmos can recognize. Imagine for a moment that you were born, raised, and lived your entire life inside a gigantic cave. You observe the shadows on the walls. You develop precise mathematical laws to predict the movement of these shadows. You create elegant equations that perfectly describe every pattern you see, but you have never had access to the outside world that is casting these shadows. Do you really know the fundamental laws of reality, or just the laws of shadows? And Tyson argues that we humans confined to this observable universe may be in exactly this situation. We have developed quantum mechanics, general relativity, the standard model of particle physics, incredibly successful theories that predict phenomena with absurd accuracy. But all of these laws were discovered by observing this specific universe, this particular energy regime, these four dimensions of space-time that we inhabit. And if you are one of those who love to question the fundamental nature of reality like I do, subscribe to the channel because we have many more fascinating scientific revelations to share with you. Tyson's provocation gains strength when we look at the history of physics, because in every era scientists have thought they were close to a final theory. Isaac Newton, in the 17th century, created laws of motion and universal gravitation so powerful that they predicted the behavior of planets, moons, comets, and projectiles on Earth with spectacular accuracy. 18th and 19th century physicists genuinely believed that Newton's laws were eternal truths of the universe, immutable and absolute, until in the early 20th century, Albert Einstein showed that Newton's laws were excellent but fundamentally incorrect approximations in regimes of high speed and strong gravity. The special and general relativity did not refute Newton in the sense that he was completely wrong, but they showed that his laws were special cases of more fundamental laws, valid only when speeds are small compared to the speed of light and when gravity is relatively weak. And so when physicists began to explore the atomic and subatomic world in the 20s and 30s of the last century, they discovered that neither Newton's nor Einstein's laws adequately described the behavior of matter on these tiny scales. Quantum mechanics was born, a theory so strange and counterintuitive that Einstein himself spent decades trying to disprove. Particles that exist in multiple states simultaneously until they are observed. Quantum entanglement, where particles separated by galactic distances remain instantly connected. Wave-particle duality, where electrons and photons behave like waves and particles depending on how you measure it. Quantum mechanics works spectacularly well. All modern technology, from computers to lasers to magnetic resonance imaging, depends on it. But it is fundamentally incompatible with general relativity in describing gravity. Then we have two theories, both extremely successful in their domains, but which cannot both be correct as fundamental descriptions of reality. And this already tells us something profound. The laws of physics that we know are not the final word. They are valid approximations in certain regimes, And Tyson takes this reasoning further in a disturbing way. He asks how many other approximations we have not yet discovered. How many more times physics will need to go through conceptual revolutions before we get close to a genuine understanding of reality? Or if this search for final fundamental laws is an illusion, a goal that always seems to be receding as we approach it like a horizon, Nettie, that we have never achieved. Cutting-edge theoretical physicists today work on theories like string theory and loop quantum gravity, trying to unify quantum mechanics with general relativity. These theories propose radical ideas like extra dimensions of space rolled up on submicroscopic scales, or that space-time is not a smooth continuum, but a granular structure on Planck-length scales that is approximately a quadrillion times smaller than a proton. These ideas are mathematically sophisticated and elegant, but here lies the devastating problem that Tyson identifies. We have absolutely no way to test these theories with current or even imaginable technology. To directly probe the Planck scale where the effects of quantum gravity would become important, we would need a galaxy-sized particle accelerator. The energies required are a quadrillion times greater than the Large Hadron Collider can achieve. So, we are developing complex mathematical theories about the fundamental nature of reality that may never be experimentally testable. And Tyson questions whether this is still physics, or has it turned in mathematical philosophy? Because historically what distinguished physics from other forms of inquiry was precisely the ability to test ideas against observable reality through experiments. But whether we reach domains of reality fundamentally inaccessible to direct observation, how do we know that our mathematical theories correspond to something real? Elegant mathematics and internal consistency are enough, or do we need empirical evidence? And this takes us to the heart of Tyson's question about whether the laws of physics are discovered or invented. When Newton wrote his equations of motion, he was discovering truths pre-existing about the universe, or inventing a mathematical system that proved useful for predicting phenomena. The distinction seems subtle, but is profoundly important. If the laws of physics are discovered, then they exist independently of us. They are fundamental features of reality that any intelligent civilization anywhere in the universe would eventually discover in the same way. But if the laws of physics are invented, they are human constructs, conceptual tools that our private minds have developed to make sense of the patterns we observe, in which case alien civilizations with different cognitive structures could develop completely different descriptions of the same reality. Physics, both equally valid and predictive but conceptually incompatible with each other, Tyson uses the example of mathematics to illustrate this point. The natural numbers 1, 2, 3, 4 exist independently of us, or are mental constructs that we invent. You can count 4 stones without having the word 4 or the symbol 4. Quantity exists objectively, but the number system we use, the decimal notation, the rules of arithmetic, these are clearly human inventions. Alien civilizations would probably use different symbols and perhaps even number bases different, but they would arrive at the same fundamental mathematical relations. Or they would, and here it starts to get strange, because there are entire branches of pure mathematics that were developed purely out of aesthetic and logical interest, without any connection to physical reality. Decades or centuries later, some of these mathematical branches proved useful for describing physical phenomena. Non-Euclidean geometries invented in the 19th century by mathematicians who were just playing around with axioms became essential to general relativity. Group theory developed in an abstract form became fundamental to quantum mechanics and the Standard Model. So the mathematics we freely invent ends up describing physical reality. Physicist Eugene Wigner called this the irrational effectiveness of mathematics in the natural sciences. Why it is irrational, why the universe should obey mathematical laws. Why pure mathematics invented without thinking about physical applications turns out to be applicable to physics. Tyson points out that this may be evidence that the universe is fundamentally mathematical in nature, or it may be that our minds have evolved to recognize mathematical patterns because organisms that recognize patterns survive better. So it is natural that we see mathematics everywhere. We are predisposed to it. A fish could think that the entire universe is wet. This discussion leads to one of the most controversial ideas that Tyson explores, the simulation hypothesis, seriously proposed by philosophers such as Nick Bostrom of the University of Oxford. The basic idea is that if it is possible for technologically advanced civilizations to create realistic computer simulations of entire universes inhabited by conscious beings, then the number of simulated universes will eventually increase, would vastly exceed the number of real universes. So statistically, it is more likely that we are living in a simulation than in the real base universe. And Tyson does not necessarily endorse this hypothesis, but uses it to make a devastating point about the limits of physics. If we are in a simulation, the laws of physics that we discovered would not be fundamental laws of reality, but rather programming rules implemented by the simulators. They would be arbitrary. The simulators could have chosen different fundamental constants, different conservation laws, different number of dimensions, and we would have no way of knowing everything. What we could study would be the internal behavior of the simulation. And here is Tyson's crux. Even if we are not in a simulation, the same argument applies. If our observable universe is just a small part of a much larger multiverse, or if there are aspects of reality fundamentally inaccessible to our observation, then the laws of physics that we know may only be local, applicable to our region of space-time but not universal. Analogies would be like trying to understand the laws of thermodynamics by studying just a glass of water. You could develop theories about how the temperature balances inside the cup, create accurate equations, but I would be completely missing the bigger picture of oceans, atmosphere, global climate, and it makes me think, from where you are watching right now, comment on your city or country. It is incredible to think that we are all connected in this same universe, trying to understand it better. And perhaps we are all equally limited by the same cognitive and observational constraints that Tyson is identifying. Modern cosmology provides concrete examples of these limitations. Our observable universe has a radius of approximately 46 billion light-years, but the entire universe is almost certainly much larger, possibly infinite. Light from regions beyond the cosmological horizon will never reach us due to the accelerating expansion of the universe. So there are galaxies, stars, planets that are in principle unobservable no matter how advanced our technology becomes. They are permanently beyond our observational reach. And if the laws of physics are different in those regions, if fundamental constants like the fine structure constant or the ratio of proton to electron mass vary from place to place in the cosmos, we will never know by just observing our cosmic neighborhood. In fact, some versions of string theory and eternal inflationary cosmology predict exactly this: a multiverse where different regions of space have different values for the fundamental constants, different numbers of macroscopic dimensions, essentially different laws of physics. Our particular region of the multiverse has the laws and constants it has not, because they are the only possible or the most fundamental, but because they are the ones that allow the existence of galaxies, stars, planets, and life. If the constants were very different, we wouldn't be here to observe them. This is called the anthropic principle, and Tyson uses this to argue that what we call fundamental laws may just be a local accident, like Earth's temperature and atmospheric pressure are local accidents in the context of the solar system. Now, some physicists hate this idea because it seems to take away the universality and necessity of the laws of physics. It turns cosmology into a kind of geography where we map out which laws apply in which regions instead of looking for universal laws. But Tyson argues that we should follow the evidence where it leads, even if we don't like the philosophical implications. And here we come to another profound point: the question of what it means to explain something in physics. Traditionally, we think we explain a phenomenon when we derive it from more fundamental principles. We explain why planets orbit the sun by deriving their trajectories from Newton's laws. We explain why atoms emit light at specific frequencies using quantum mechanics. But at each level of explanation, there is always another why. Why gravity follows an inverse square force law. Why particles have the masses that have. Why the speed of light has the value of approximately 300 million meters per second. We answer these whys by invoking deeper theories, but eventually we reach a point where there is no further explanation. We have to accept certain things as given, fundamental axioms, and the question that Tyson raises is whether this final point is a genuine feature of reality, a set of brute facts with no further explanation, or whether it is just a limit of our cognitive or observational capacity. Perhaps there is a deeper explanation, but our mind is not capable of to understand it. Consider that our brains evolved to help our ancestors survive on the African savannas, finding food, avoiding predators, cooperating in social groups. There was no evolutionary pressure to understand quantum mechanics, or general relativity, or string theory. The fact that we can understand these topics is almost miraculous. But perhaps there are levels of complexity or abstraction beyond what our brains can process. No matter how much we study, Tyson uses the analogy of trying to teach quantum mechanics to a dog. It's not that the dog is stupid, it's that their brain simply doesn't have the cognitive architecture necessary to understand such abstract concepts. And maybe we're the same situation in relation to even more fundamental theories. There may be a final theory of everything that unifies all forces and particles and explains all fundamental constants. But this theory could be so abstract and mathematically complex that it transcends our cognitive capacity. We would be trying to understand something beyond the design limit of our brain. And if that is the case, then the laws of physics that we know are not necessarily wrong but are perhaps simplifications. Approximations that our mind can capture from a much richer and more complex reality. Physicists and philosophers have tried to quantify this idea. The neuroscientist and philosopher David Chalmers has suggested that perhaps for each level of intelligence, there is a corresponding set of accessible truths. Humans can understand truths that require abstract reasoning up to a certain level of complexity. More advanced intelligences, be they aliens or future artificial intelligences, could access even deeper truths, and this implies that human physics may not be the end of history. There may be alien physics or post-human physics that go beyond what we can understand today. Tyson also points to more practical and immediate limitations. Our instruments of observation, no matter how sophisticated, always have limits of sensitivity and resolution. We cannot measure anything with infinite precision. There is always experimental uncertainty. And in some cases, the quantum nature of reality itself imposes fundamental limits on what we can measure. Heisenberg's uncertainty principle tells us that we cannot simultaneously know the position and momentum of a particle with arbitrary precision. It is not a technological limitation, but a fundamental characteristic of quantum reality. And these limits of measurement propagate to limits of knowledge. If we cannot measure certain quantities with perfect precision, our theories based on these measurements will always have a degree of uncertainty. And perhaps in some regimes, this uncertainty becomes so great that we can no longer distinguish between competing theories. Consider the cosmological constant or dark energy, which is causing the accelerated expansion of the universe. Current measurements suggest that approximately 68% of the universe's total energy is in the form of dark energy, but we don't know what it is. We don't know if it is actually a cosmological constant, as Einstein proposed, an exotic form of energy called quintessence, a modified gravity effect, or something else entirely. And current observations are not precise enough to distinguish between these possibilities, then we have multiple theories all compatible with the data. And we may never achieve the observational precision needed to decide between them conclusively. This is another example of what Tyson is pointing out: practical limits of empirical physics. Now, some scientists argue against Tyson's pessimism. They point out that throughout history, we have repeatedly surpassed limits that seemed fundamental. Before the development of telescopic astronomy, we thought we could never know the chemical composition of stars. They are too far away. How could we analyze their matter? Then we discovered the spectroscopy, and today we know the chemical composition of stars billions of light-years away with incredible precision. Before quantum mechanics, we thought we would never understand the internal structure of atoms, but we have developed theoretical and experimental tools that have allowed us to probe subatomic scales. So perhaps the limits that Tyson identifies are temporary, not fundamental. Perhaps future conceptual and technological revolutions will give us access to aspects of reality that today seem permanently out of reach. And that is a genuine possibility that Tyson recognizes. He is not saying that we have definitely reached the limit of possible knowledge. It is saying that we must be humble about our claims to understand the fundamental laws of the universe. Because history teaches us that theories that seemed definitive in the past were eventually surpassed or recontextualized, another aspect of Tyson's questioning involves the very nature of the mathematics we use in physics. Modern physics relies heavily on and of continuous mathematics. Calculus, differential equations, functional analysis, all assume that quantities can vary continuously, that space and time are infinitely divisible. But is this really true? Or is it just a convenient approximation? Growing evidence from theories of quantum gravity suggests that at Planck scales, space-time may be discrete, granular, not continuous. If this is the case, then the entire mathematical structure of continuity-based physics would be an approximation valid only at larger scales. Fundamental physics would be inherently discrete, perhaps based on structures algebraic or information theory rather than continuous mathematical analysis. And this would require completely reformulating our fundamental laws using entirely different mathematical language. Some physicists like Stephen Wolfram and others working on computational approaches to physics argue exactly this: that the universe at its most fundamental level operates as a discrete computational system, executing simple algorithmic rules that generate all the complexity we observe. If this view is correct, continuous differential equations we use today are emergent approximations of underlying discrete processes, just like thermodynamics, with its variables. Continuous processes, such as temperature and pressure, emerge from the discrete behavior of individual molecules. Tyson does not necessarily endorse this specific approach, but uses it as an example of how radically different fundamental physics can be from the physics we know. If this conceptual revolution happens, we will look back on our current equations in the same way we looked at Aristotelian physics, not exactly wrong, but fundamentally limited by unexamined assumptions about the nature of reality. So what Neil Tyson is really arguing is not that there is a specific theory that defies the laws of physics in the sense of proposing new mechanisms or phenomena, but which is challenging the idea that the laws we know are genuinely fundamental or universal, is raising deep epistemological questions about what we can know, how we can know, and whether there are intrinsic limits to the scientific enterprise that we can never transcend. And these questions make many scientists uncomfortable because they touch on the foundations of what we do. If part of reality is in principle unobservable, can we still call it science? If our most fundamental theories cannot be tested experimentally, what distinguishes them from philosophy? Speculatively, if our mind has cognitive limits that prevent complete understanding, is it worth continuing to seek more fundamental theories? Tyson argues that yes, it is worth it, Because even if we never achieve complete and final understanding, each step along the way expands our knowledge and capabilities. Newton did not have the final theory, but his contributions were immensely valuable. Einstein went beyond Newton, but also did not arrive at a final theory. And each generation of physicists contributes to a progressively deeper understanding, even if complete understanding remains eternally out of reach. It is like climbing an infinitely high mountain. You never reach the top, but the view gets better and better the higher you climb. And Tyson also emphasizes that recognizing our limits is in itself a form of knowledge. Knowing what we don't know and what we may not know is valuable. It protects us from intellectual arrogance and keeps us open to new possibilities. Throughout history, the biggest scientific mistakes have come from overconfidence, that we already had it all figured out. Late 19th century physicists thought that physics was essentially complete. There were just a few details left to get right. So came the quantum and relativistic revolution that showed how wrong they were. Epistemological humility could protect us from making the same mistake again. And here we come to something that Tyson emphasizes repeatedly: the difference between established science and scientific speculation. When he questions whether the laws of physics are universal, he is not questioning that these laws work extraordinarily well within their domains of validity. General relativity predicts the behavior of black holes, gravitational waves, gravitational lenses with phenomenal accuracy confirmed by countless observations. Quantum mechanics and the Standard Model predict particle interactions with precision to 12 decimal places. These theories will not simply disappear. Any future theory will have to reduce them to special cases or approximations. Just as relativity reduces Newton to a low-speed approximation, so we are not questioning the practical validity of current physics, but rather its claim to absolute fundamentality. And this is a crucial distinction that often gets lost in discussions. Popular on these topics, Tyson is careful to keep this distinction clear. Another dimension of questioning involves the very logical structure we use to do science. Scientific method, as we practice it, involves forming hypotheses, making testable predictions, performing experiments, refining theories based on results. This method presupposes that nature is regular, that repeated experiments under the same conditions will give the same results, that induction works, that we can infer general laws from particular cases. But these assumptions cannot be proven scientifically. They are philosophical axioms that we accept because they work. The philosopher David Hume in the 18th century pointed out the problem of induction. There is no logical justification for assuming that patterns observed in the past will continue in the future. Just because the sun has risen every day so far does not logically guarantee that it will rise tomorrow. We accept this out of habit and utility, but not by logical proof. Tyson uses this to show that even the scientific method has foundations that are not scientifically justifiable. They are pragmatic choices, and perhaps there are other equally valid methods of investigating reality that have not occurred to us because our mind is structured in a certain way. Now, this may seem very abstract and philosophical, so let's bring back concrete physics. One area where the limitations that Tyson discusses clearly manifest themselves is the cosmology of the very early universe. Current theories suggest that our universe went through a period called cosmic inflation in the first few moments after the Big Bang. During approximately 1/1,000,000th of a trillionth of a trillionth of a second, the universe expanded exponentially fast, growing from subatomic size to perhaps the size of a grapefruit or larger. This theory explains many observed properties of the universe, such as its large-scale uniformity and the structure of quantum fluctuations that gave rise to galaxies. But here is the problem. Everything before inflation is completely inaccessible to observation. Any information about the initial state has been erased by inflationary expansion, so we cannot scientifically test hypotheses about what caused the Big Bang or what existed before, if it even makes sense to talk about before. We are permanently blocked from having empirical evidence on these questions. Some physicists propose ideas such as baby universes sprouting from black holes, or our universe being a quantum fluctuation of nothingness, or being eternal without beginning. But neither of these ideas can be tested against alternatives, are speculations that go beyond empirical science, and Tyson argues that we should be honest about this. We can explore these ideas mathematically and philosophically, but we should not confuse them with established scientific knowledge. Similarly with the ultimate fate of the universe, current observations suggest that the expansion of the universe is accelerating and will continue to accelerate forever. In approximately 100 trillion years, all the galaxies beyond our local group will have moved so far apart that its light will never reach us again. The observable universe will shrink to contain only the Milky Way and its close neighbors that will have merged into a single supergalaxy. All the stars will eventually burn their fuel. Black holes will evaporate through Hawking radiation on timescales of Google years, and the universe will become cold, dark, and essentially dead. But these predictions assume that the current laws of physics remain constant for these unimaginable eons. And we have no way of knowing if this is true. Perhaps there are physical processes or phase transitions that only happen on extremely long time scales that will completely transform the universe in ways we cannot predict. Then again, we are making huge extrapolations based on untestable assumptions. And the more we reflect on these questions, the more we realize the wisdom in Tyson's caution. Physics is incredibly successful within its domain, but that domain has boundaries, observational boundaries, conceptual boundaries, possibly cognitive boundaries, and recognizing these boundaries is not defeatism, but realism. It also makes room for humility and wonder, because it means that the universe is probably much more mysterious and surprising than our current theories capture. There are aspects of reality that go beyond what we can imagine, and this is both humbling and inspiring. Some of the greatest scientists in history have expressed similar sentiments. Isaac Newton, near the end of his life, wrote that he felt like a boy playing on the beach, occasionally finding a smoother stone or prettier shell than usual. While the great ocean of truth lay unexplored before him, Albert Einstein wrote that the most incomprehensible thing about the universe is that it is understand level, expressing surprise that our minds can understand anything about the cosmos. Richard Feynman, famous for his work in quantum electrodynamics, said that if you think you understand quantum mechanics, you don't understand quantum mechanics. Recognizing that nature is fundamentally stranger than our intuitions, then Tyson's questioning is part of a long tradition of scientific humility expressed by the greatest thinkers. And if these discoveries blew your mind as much as mine, leave your like. Subscribe to the channel and turn on notifications because we have many more mysteries of the universe to unravel together, because what we are exploring here goes beyond isolated scientific facts. We are questioning the very nature of scientific knowledge, its powers and limitations, and this has profound implications not just for physics, but for how we think about ourselves and our place in the cosmos. If our minds evolved to survive on African savannas and only coincidentally managed to understand some cosmology and particle physics, then we are not neutral, objective observers of the universe, but deeply intertwined participants in it. Our view of the cosmos is inevitably colored by our particular perspective, sensory limitations, cognitive structure, even by the language and culture we use to describe discoveries. Different cultures throughout history have developed different cosmologies, different ways of making sense of the heavens, and although modern physics with its experimental method has converged on universally accepted descriptions within the scientific community, perhaps this convergence says more about the universality of certain human cognitive structures than about the inevitability of the physical laws we have discovered. An alien civilization with different senses, which perceives different bands of the spectrum electromagnetic, who live in a radically different environment, could develop physics that seems completely alien to us, even though they describe the same physical universe. Their fundamental axioms, basic quantities they measure, even mathematical structure they use could be different from ours, and both physics could be correct in their own terms. Different maps of the same territory using different coordinate systems and conventions. This raises fascinating philosophical questions about scientific objectivity. We often think of laws of physics as objective truths about the universe, but whether different intelligent observers can arrive at radically different but equally valid descriptions, perhaps objectivity is more subtle than we thought. Perhaps what is objective is not the specific laws, but rather the existence of regularities that can be captured by mathematical structures. The details of these structures being part convention and part discovery, physicists working on quantum field theory and string theory already encounter this situation. There are multiple mathematically equivalent formulations of the same physical theory. Different representations that look very different on the surface, but make exactly the same experimental predictions. Which one is the true description of the reality? Or does this question make no sense? Perhaps they are all equally true, different ways of looking at the same underlying structure. And if this is so for our current theories, how much more will it be for hypothetical ultimate theories? Tyson also points to the role of technology in expanding and limiting our knowledge. Each new generation of telescopes reveals phenomena that we could not observe before. When Galileo pointed his telescope at Jupiter and saw moons orbiting another planet, it was a revelation that transformed our understanding of the solar system. When Edwin Hubble in the 1920s used the Mount Wilson telescope to measure distances to spiral nebulae and discovered that they were entire galaxies beyond the Milky Way, the known universe expanded 1,000,000 times. When the Hubble Space Telescope captured the ultra-deep field showing thousands of galaxies in a tiny patch of sky, we realized that the universe contains hundreds of billions of galaxies each, with hundreds of billions of stars. And now, with the James Webb Space Telescope, we are observing galaxies that formed just a few 100 million years after the Big Bang. Seeing the universe in its infancy, each technological advance reveals more complexity and mystery, but also each instrument has its limits. We cannot see beyond the cosmological horizon, no matter how powerful our telescopes are. We cannot resolve structures smaller than the wavelength of the light we use. We cannot detect particles that interact very weakly with normal matter. So our picture of the universe will always be limited by the tools we can build. And that is, these tools in turn are limited by the laws of physics and the resources available. There are fundamental engineering limits. You cannot make an optical telescope larger than a planet because there would be no structural material strong enough to support it. You cannot accelerate particles to arbitrary energies because it would need infinite amounts of energy. Then there are regions of physical parameter space that are permanently inaccessible to direct experimental investigation. What Tyson emphasizes is that we must recognize these limitations when making claims about the fundamental nature of reality. When we say that we have discovered the laws of physics, we should be more precise and say that we have discovered laws that describe physical reality well within the domain. We can observe and test. This is not false modesty, but intellectual precision, and it keeps us open to the possibility that there are deeper layers still undiscovered. Now, some may argue that this approach is overly skeptical, that if we take Tyson's skepticism to its logical conclusion, we end up in solipsism, where we cannot know anything with certainty. But Tyson is not advocating radical skepticism. He is advocating calibrated skepticism, recognizing what we know well, what we know less well, what is speculative, and what is beyond our current or perhaps permanent ability to know. This nuance is crucial but often lost in popular discussions about science. We tend to talk about physics as if everything is equally well established, but it is not. There are things we know with overwhelming certainty, like the speed of light, the charge of the electron, the structure of DNA. These have been measured countless times under countless conditions, and they always agree there are things we understand very well theoretically and empirically, such as quantum mechanics of atoms and molecules, fluid dynamics, thermodynamics. These theories have clear domains of validity and make accurate testable predictions within those domains. There are more speculative but still empirically grounded theories, such as cosmic inflation, which explains observations but has not been directly tested. And there are highly speculative ideas such as string theory and the multiverse, where empirical evidence is at best indirect and at worst completely absent. Tyson argues that scientists should be much clearer in communicating these distinctions to the public. When we present string theory, we should emphasize that it is elegant but untested mathematics. When we talk about the multiverse, we should make it clear that it is theoretical speculation, not established fact. This honesty does not weaken science, but strengthens it. It shows that science is an ongoing process of discovery, not a fixed set of dogmas, and it allows the public to better understand how science really works. With all its uncertainties and debates, this transparency is also important because some of the questions Tyson raises have practical implications. For example, debates about the interpretation of quantum mechanics. There are at least a dozen interpretations that are mathematically equivalent but conceptually different from quantum formalism, the Copenhagen interpretation, many worlds interpretation, de Broglie-Bohm interpretation, relative states interpretation, consistent history interpretation, all make the same experimental predictions, so we cannot decide between them empirically, but they have radically different implications about the nature of reality. Many worlds suggests that each quantum measurement creates branches of the universe where all possible outcomes occur. De Broglie-Bohm suggests that particles have defined positions guided by a pilot wave. Copenhagen suggests that reality is fundamentally indeterminate until measurement collapses the wave function. These are not just semantic differences, but radically different views of the ontology of the physical world, and choosing between them may eventually have practical consequences as we develop advanced quantum technologies, quantum computing, quantum communication, quantum sensors. Different interpretations may suggest different engineering approaches, so these philosophical questions that Tyson raises are not just academic but potentially relevant to future technology. Similarly, debates about the nature of space-time. Is space-time a fundamental entity or something emergent from more basic degrees of freedom? This question is central to quantum gravity and could affect how we think about cosmological computation, interstellar travel, even the possibility of manipulating space-time. If space-time is fundamental, then it is immutable beyond gravitational curvature. But if it is emergent, perhaps we can in principle engineer it in ways that today seem impossible. So these are not just idle speculations, but questions that may eventually matter. In practice, Tyson often emphasizes that keeping an open mind to radical possibilities is part of what makes science exciting. If we think we already know everything, then there are no more discoveries to make. But if we recognize the vastness of the unknown, then each day brings the possibility of new insights, and history is full of examples of discoveries that were completely unexpected. Of microwaves detected by Arno Penzias and Robert Wilson in 1965, as they tried to eliminate noise from their antenna, in each case the scientists were doing something completely different when they stumbled upon fundamentally new phenomenon. This suggests that there are still fundamental discoveries waiting for us, things we are not looking for because we can't even imagine they exist. And maintaining epistemic humility makes us more receptive to these surprises when they appear. Now, all this we have discussed may seem discouraging, If there are all these limits to what we can know, what is the point to continue doing physics? But Tyson argues exactly the opposite. Recognizing limits makes the discoveries we make even more precious and impressive. Despite being evolved monkeys on a small planet orbiting an ordinary star in a typical galaxy, we have managed to discover that the universe is approximately 13.8 billion years old, that it is composed of atoms made of quarks and electrons, that it is governed by 4 fundamental forces, that it began in an extremely hot and dense state and has been expanding ever since, that it contains structures on all scales from particles, from subatomics to superclusters of galaxies. This is an extraordinary intellectual achievement, and every bit of this knowledge has been gained through hard work, careful observations, ingenious experiments, creative thinking. The fact that our knowledge is limited does not diminish what we have achieved, but makes it all the more remarkable. We are part of the universe that has become aware of itself. Atoms of carbon and oxygen and nitrogen arranged in such a way that we can gaze at distant stars and wonder where they came from. This is profoundly wonderful regardless of how many questions remain unanswered. And perhaps unanswered questions are an essential part of what makes science meaningful. If we knew everything, there would be no more sense of discovery or wonder. Mystery is what pulls us forward. Each answer we find reveals new, even deeper questions, and this process can continue indefinitely. There will always be more to discover, more to understand, more to wonder. And Tyson celebrates this. He does not see the limits of knowledge as sad barriers, but as invitations to humility and wonder. When we look up at the night sky and see thousands of stars, each potentially with their own planets, when we think about the trillions of galaxies beyond our vision, when we contemplate the elegant mathematical laws that govern it all, we should feel not arrogance that we understand, but reverence for the vastness of what remains unknown. This perspective also reminds us of our responsibility. We are, as far as we know, the only species on this planet capable of doing science, of systematically investigating the nature of reality. This gives us a unique responsibility to continue that search, to pass on accumulated knowledge to future generations, to protect civilization's ability to do research basic, because each generation receives a heritage of knowledge from those who came before and has a responsibility to expand and pass on that heritage, and part of that responsibility is to be honest about what we know and what we don't know, not to exaggerate certainties, not to hide uncertainties, to present science as it really is, a fallible but self-correcting process of progressively approximating the truth. So when Neil Tyson raises these profound questions about the limits of the laws of physics, he is not undermining science, but advocating a more honest and humble way of doing and communicating science, a way that recognizes both the extraordinary triumphs and the inevitable limitations of the scientific enterprise. And this message resonates because it touches on something deeply human, the desire to understand our place in the cosmos, combined with the awareness of our smallness and mortality. We want to know where we came from and where we are going, what the universe is, and why there is something rather than nothing. These are questions that humans have asked for millennia. All cultures have developed cosmologies trying to answer them. What makes modern science special is not that it has definitive answers, but that it has a method to progressively refine the responses that we have, to distinguish what we know from what we just think we know, to admit ignorance when necessary, and that is a form of wisdom. To know what you know, to know what you don't know, and to know the difference between the two. Socrates said he knew nothing, and that made him wiser than those who thought they knew but didn't. In modern science, we maintain this Socratic spirit, always questioning, always testing, always open to the possibility that we are wrong. And the more we learn about the universe, the more we realize how little we know. The circle of knowledge grows, but so does the circumference of contact with the unknown. Each answer generates new questions, and that is beautiful, not tragic, because it means that we will never run out of mysteries to explore, no boundaries to push, no wonders to discover. The universe is inexhaustible in its capacity to surprise us, and as long as there are curious minds, there will be science. There will be this wonderful search for understanding that defines what it means to be human. So perhaps Tyson's true message is not that the laws of physics are inadequate, but that the universe is vaster, stranger, richer in possibilities than any set of laws can fully capture. That we are just beginning to scratch the surface of a deeply mysterious reality, and that this is the most exciting adventure we can embark on, to explore the limits of possible knowledge, and in doing so discover not just about the universe, but about ourselves, about what it means to be a species capable of asking questions about the cosmos. This is the journey that scientists around the world continue today, in observatories and laboratories and universities, making ever more precise measurements, developing ever more accurate theories, sophisticated, exploring regimes of energy and temperature and density that have never been accessible before. Each small advance is a victory against ignorance. And collectively, these advances paint an increasingly detailed picture of reality, even if the picture is never complete, even if there always remain unexplored corners and unsolved mysteries. Because ultimately what Tyson is inviting us to do is keep alive the flame of curiosity and humility. Curiosity to keep questioning and exploring. Humility to admit when we have reached the limits of what we can know for sure. And this combination of curiosity and humility is the essence of the scientific spirit. It is what has allowed us to go from caves to the stars, understand atoms and galaxies, develop technologies that have completely transformed human existence. And, if we continue in this spirit, who knows what we will discover in the coming decades and centuries? Perhaps we will find answers to questions that seem impossible today. Perhaps we will develop new forms of inquiry that transcend current limitations. Or perhaps we will discover that some questions really are beyond our ability to answer, but even that would be a valuable discovery, a mapping of the limits of knowledge possible. And in any scenario, the journey will be worth it because it will expand our understanding and feed our sense of wonder. So keep questioning, keep learning, keep marveling at the cosmos, because that is the legacy that Neil Tyson and all the great scientists and thinkers leave us. Not definitive answers, but better questions. Not absolute certainty, but progressively deeper understanding. Not the end of discovery, but the infinite invitation to keep exploring. And that is more precious than any final answer could be, because it means the adventure never ends. There is always more to come. Discover, more to understand, more to celebrate about this extraordinary universe we call home.